Hello, friends. Mr. Burrell here. We're in our unit talking about linear functions. And today in lesson 1.2, we're going to be talking about graphing linear functions. Okay, so let's get right to it. By the end of this lesson, hopefully you are able to graph some linear equations and then solve a system of linear equations algebraically and graphically. We'll talk about how to solve a system of equations in both of those ways. So just a little bit of linear equation humor for you. Y equals mx plus b is my favorite one-liner. And don't forget to always label your axes or your axes. Good. So to start, some definitions. First of all, when I'm talking about a graph, just a picture, a visual representation of the function showing the change between the x variables, the independent variables, and the y variables, the dependent variables. Okay, that's what a graph is, just a visual representation of my function. Slope-intercept form that we're going to use a fair amount today is y equals mx plus b. You're probably familiar with this form and recognize that m represents the slope of the line and b represents the y-intercept, or where that line crosses the y-axis. And then lastly, a system of equations is two or more, 4 or 5, however, equations to be solved together where the solution is the intersection point. And the examples we're going to bring up with a system of two equations, the solution is the point, the coordinate point on the graph where those two lines intersect. Okay. So let's go ahead and start by practicing graphing some lines. This equation is already in slope-intercept form, y equals mx plus b, where this is the y-intercept and this is the slope. So let's draw it. The y-intercept is 3. So I know the line crosses this point right here on the y-axis. The slope is negative 4/3. When I'm talking about slope, I'm talking about rise over run. So my rise is down 4 and my run is right 3. So I'm going down 4, that's my rise, and right 3. So right there is 2 of my points. If I go down 1, 2, 3, 4, and right 1, 2, 3, again, there's another point. If I go up 4 and left 3, here's another point. So my line, pardon the roughness of my drawing, looks something like this. Okay. For this equation, it's not quite yet in slope-intercept form. So I need to change that. I need to get y by itself. So I'm going to go ahead and add 5x on both sides to start with, leaving me with 2y equals 5x minus 4. And then I'm going to divide everything on both sides by 2, leaving me with y equals 5/2 x minus, and then 4 divided by 2 is 2. Now it's in slope-intercept. So my y-intercept is negative 2, and my slope is up 1, 2, 3, 4, 5 over 1, 2. 1, 2, 3, 4, 5, left 2. My line's going to look something like this. Okay, so that's how I graph a line once it is in slope-intercept form. Now, let's talk about solving a system of equations. First, we're going to talk about solving them algebraically by substitution or elimination. This is something that you've learned before, but it might have been a minute. So we're going to discuss it. What does it mean to solve a system of equations by substitution versus elimination? In order to solve a system of equations by substitution, that means I have two equations, and here they are. In order to solve by, these are actually swapped. This is by elimination, and this other one is by substitution. In order to solve a system of equations by elimination, there you go, I need to manipulate the equations in such a way that when I add the two equations together, one of the variables goes away. It's eliminated, it disappears. So I'm left with just a single variable, a one variable equation that I can solve. So take these two equations, for example. I have 5x plus 7y equals 9 and negative 5x plus 4y equals 13. Notice how already these equations are in a position where if I add them together, one of the variables is going to disappear. For example, 5x and negative 5x added together is 0. It cancels out. 7y plus 4y is 11y. 9 plus 13 is 22. Now I have a single variable equation for which I can solve for y. In order to solve for y, I would divide by 11 on both sides. giving me y equals 2. That's my first solution. The y coordinate of my solution is y equals 2. So now, in order to solve for x, I'm going to choose either of these equations. I'm going to choose the first one and substitute 2 in for y. So instead of putting in a y, I'm going to put in a 2. So I'm left with 5x plus 7 times 2 equals 9, which simplifies to 5x plus 14 equals 9. Now, again, I have a single variable equation where now I can solve for x. I would subtract 14 on both sides, giving me 5x equals -5. Divide by about 5 on both sides, and I get x equals -1. In writing that solution as a point, as a coordinate point, I would have -1, 2. So on my graph, the point on the graph that represents the solution is -1, 2. And if I put -1 in for all my x's and 2 in for all my y's, the top equation better equal 9, and the bottom equation better equal 13. Okay, that's how I solve a system of equations using elimination. Now let's talk about solving by substitution. When I'm talking about solving a system of equations by substitution, I'm going to isolate a variable and plug what that variable is equal to in its entirety in for that corresponding variable's value in the other equation. Let me explain. Notice how in these two equations, I have one equation where one variable is isolated. Y equals 1/2 x minus 4. Well, I can take this whole expression that's equal to y and plug it in for the value of y in this first equation, which I've done here. 3x plus 2, and then instead of y, I wrote in parentheses 1/2 x minus 4 equals 8. Now I've eliminated one of the variables. All I'm left with is x's. So I can go ahead and distribute the 2 into both of these, leaving me 3x plus x, because 2 times 1/2 is 1x, and then 2 times -4 is -8 equals 6. 3x plus x is 4x. If I add 8 onto this other side, I end up with 4x equals 16. Divide by 4 on both sides, I end up with x equals 4. That's the x coordinate of my solution. Now that I have the x value, I can plug that value in for x in one of these equations. Doesn't matter which one, I just chose the second one because it's easier. I get y equals 1/2 times 4 minus 4. 1/2 times 4 is 2, minus 4 is -2. So my solution as a coordinate point is 4, -2. And if I plug 4 in for all my x's and -2 in for all my y's, those equations better balance. Okay, so now let's practice. I have a couple equations here, -3x or plus 2y equals -2, x equals 4 minus y, and then I have the example 6 equation. I want to solve one of these by elimination and one of them by substitution. You notice right now, both of these equations kind of lend themselves to be solved by elimination, but so you get practice with both. I'm going to solve this first one by, or I meant to say substitution. Both of these lend themselves to be solved by substitution. I'm going to solve the first one by elimination. So in order to do that, I want since this top equation has x and y on both sides, in the bottom equation, I'm going to get x and y on the same sides. So I'm going to have x plus y equals 4. Then this top equation, let me just rewrite it down below here. -3x plus 2y equals -2. So if I were to add these two equations together right now, it wouldn't really help me because I'm not going to eliminate a variable. So I'm going to have to manipulate one of these equations in such a way so that when I add them together, one of the variables disappears. So notice here I have a positive 1x and then I have -3x. So if I were to multiply this x by a positive 3, 3x and -3x when added together would cancel out and give me 0. So let's multiply this whole expression by 3. Okay, and I'm going to rewrite that underneath it. 3x plus 3y equals 12. Okay, now when I add these two equations together, -3x plus 3x goes away, it's 0. 2y plus 3y is 5y. -2 plus 12 is 10. Now I can just solve for y because it's the only variable that's left. I divide by 5 on both sides and I get y equals 2. There's the y coordinate of my solution. Okay, well now I'm going to go ahead and plug this value of y that I found, which is 2, in for y in one of these equations. It doesn't matter which one. I'm going to go ahead and plug it into this equation right here because I feel like that's going to be easiest to solve. x equals 4 minus 2, because y is 2. 4 minus 2 is 2. So my solution is x equals 2 and y equals 2, or as a coordinate point, 2, 2. Okay? So I solved that one using elimination. Let's solve example 6 by substitution. I have y equals 4x plus 1, so I can plug this whole expression in for y in the second equation. 4x plus 1 minus 3 equals 4x. Now there's just x's. I can solve for x. So let's see, 1 minus 3 is -2. Notice what starts to happen here. I'm going to go ahead and subtract 4x on both sides. 4x minus 4x cancels out. And on this side, I'm left with 4x minus 4x, which is 0. Interesting. All the x's went away, and I'm left with -2 equals 0, which doesn't even make sense. -2 doesn't equal 0. So when I have this situation, that means there's no solution. There's no value for x and y together that's going to satisfy both of these equations. Okay, so we've talked about solving these systems of equations by elimination and by substitution. Now let's solve those same systems of equations by graphing. Okay, so just for reference, the solution here was 2, 2. The solution here was no solution. We'll see what that looks like in graph form in just a minute. So when I'm solving a system of equations by graphing, this is what I'm looking for. I'm just going to write a couple of lines just for reference. So say I have this line right here, and I have another line. We call it this line right here. The solution to this system of equations is the point where those two graphs, those two lines intersect. So like if these were my two functions graphed on this coordinate grid, the solution would be -2, 1. X is -2, y is 1. That's how I solve a system of linear equations by graphing. So let's do that. In order to solve these by graphing, first of all, I need both of them in slope-intercept form. So let's take this first one. In order to put this first one in slope-intercept form, I need to get y by itself. So I would add 3x on both sides, giving me 2y equals 3x minus 2. Then I would divide both sides by 2, leaving me y equals 3/2 x minus, and then 2 divided by 2 is 1. So flashing back to the beginning of this lesson, -1 is my y-intercept, and I go up 3 over 2, up 3 over 2, down 3, left 2, etc., etc. So this is my graph. Okay. Now let's solve the other equation for y. Let me change colors here. Graph that function and then see where the two graphs intersect. So we'll go ahead and add y on both sides, which gives me y plus x equals 4. I just did that to get y on the left and make it positive, you know. Then I'm gonna go ahead and subtract x, wow, on both sides, leaving me with, let me write this right here, y equals -x plus 4. So my y-intercept is +4. My slope is -1, so I go down 1 over 1, down 1 over 1, down 1 over 1, etc., etc. So there is my second line. And you can see that the point where they intersect is indeed 2, 2. So the solution to that system of equations is 2, 2. X equals 2, y equals 2. Okay, let's solve example number 6 by graphing. Try to be thinking in your brain of what you think these two graphs are going to look like that would yield no solution. So this first equation is already in slope-intercept form. So my y-intercept is 1. I go up 1, 2, 3, 4 over 1, down 1, 2, 3, 4, left 1. And that kind of gives me, pardon my graph, that line right there. Let me change colors for the second one. This one I'm going to have to solve for y. So I'm going to add 3 on both sides, giving me y equals 4x plus 3. So I have y-intercept of 3, and I go up 1, 2, 3, 4 over 1, down 1, 2, 3, 4, left 1, down 1, 2, 3, 4, left 1. And looks something like this. Obviously, my pictures aren't great, But what do you notice about these two lines? Why is it that they have no solution? Well, notice how both of these lines had the same slope. Both of these lines have a slope of 4, going up 4, over 1, up 4, over 1, over and over and over again. But they have two different starting points. One started on the y-axis at 1, one started at 3. So these two lines, because they have the same slope, actually never touch. They will never have an intersection point, which means they will have no solution. If I happen to get two equations of the same line, so say I graphed this line and I had another line that went right across the top of it, that means I would have infinitely many intersection points, meaning my solution would be all real numbers, or I'd have infinitely many solutions. So those are the different situations that can happen. So there's a couple of examples of solving a system of equations by graph. And that's it. Hopefully now you can graph a linear equation and solve a system of linear equations, both algebraically and graphically. Thank you for being here, and I hope that you had as much fun as I did.